lab we're going to be continuing today. So with that, some properties of water are coming out today, and what you'll see is that for homework you have reading guide 15 and 16. My job is to answer most of the questions on reading guide 15 right now, so take good notes so that you understand. You can transfer that into your reading guide when you get home. Okay? So, empirical formula, EJ's group, your table. H2O, right? Simplest ratio we can make is H2O. Robbie's group, molar mass. Approximately 18 what? Wait. What's the units? Per mole, okay. Grams per 1 mole. Ionic or covalent? Jillian's area over there. Little small group there. It's definitely covalent. And tell me how you know it's covalent. Okay, it's a bond between an H and an O, or an O and an H, based on which way you look at it. But regardless, this is a bond between the two nonmetals in this case, and it's not including anything that's we term a polyatomic ion. Your guys' biggest misconception yesterday, when you were trying to figure out if ammonium nitrate was ionic or covalent, you guys were like, oh, it's all nonmetals. And I was like, true story, but not right. So then you had to kind of think outside the box. Like, can't nonmetals come together to make ions? Yes, they can. There's ammonium. There's nitrate. Well, those are two ions, and ions come together to make what kind of compounds? Ionic, because that's what the term ionic means. It means it contains ions. So that's a don't just go with the general rule of thumb as nonmetals covalent, because sometimes you get in a place like this. All right, what kind of polarity are we dealing with right here? It is polar, right? And so polar means what again? When you say partial charge, partial what charge? What kind of charges do we have? There's only two. Right, so there's a partial negative and there's a partial positive charge up among the water molecule itself, which gives us that polarity, like opposite ends of the poles of the Earth has a polarity. Molecular geometry, meaning the shape. This group up here. Do you remember? You might have to draw it. One of them, you gotta make a choice.
Bent.
It is bent, thank you. And so the polarity kind of gives it away. How does this look when you draw it on paper? Don't say bent, I know that. Tell me how you would actually draw it. So I want you to draw the Lewis dot structure. I'm sorry, I'm probably not phrasing that well. Draw the Lewis dot structure for water. Take about 2 seconds. All right, Kyle, tell me what you got, man. Nope. Here, I'll pass it back to you. You did. Passed it to me, I passed it back.
I have another skip card.
Give me your gut instinct here. There's only 2 letters in it. Okay, so but how many H's?
2 H's.
2 H's. Do I connect the H's together?
No, you can't.
Connect it to the O. Okay, and I'm drawing it bent because that's how I was told to. All right, and then Kyle's telling me in his mind, he's saying you're missing some lone pairs. Thanks, Kyle. There's 2 lone pairs here because oxygen. Say again?
You should just always read mine.
Okay, yeah, I was trying to give you a chance there. Okay, so we have a problem here, right? We didn't think about this first, but whenever you're drawing a Lewis dot model, you should always count the valence electrons. Oxygen's in group what? 6, so oxygen carries 6 valence electrons. Each of the hydrogens are in group 1, so each of them carry 1 valence electron. So that's 1 plus 1 plus 6 equals 8 valence electrons, which then allows us to see how this is portrayed on the Lewis dot diagram as 2, 4, 6, 8. That's great. Why does hydrogen not have octet? Right, and that's, what do we call that rule?
I know the rule.
Okay, so octet's the 8 rule, right? Duet's going to be for 2 valence electrons because it's so tiny. Hydrogen's going to accommodate 2, and helium, and then there's a couple of others that have exceptions to the octet rule. Octet's only true about 50% of the time, so I don't really know what we call it a rule. It's more of a suggestion. Okay, what are some properties of water? Shout them out that you just know from everyday life. Go for it, Caroline.
I'm taking a crop.
I'll come back to you. Give me something else.
It's the universal solvent.
Okay, ooh, it's a great solvent. Okay, can I get something else? So the density differs, is greater as a liquid versus as a solid. What else? Okay, so liquid at room temperature. Yeah. Okay, so freezing point at 0 Celsius at normal atmospheric pressure.
It boils at 100.
Okay, you guys are giving me all of the physical properties. Can I get something else too? What can water? Let's see here. How does it get from the roots of a plant up to the top of the leaves of a plant or a tree? Okay, that and say again? Okay, so transpiration is the process of releasing it through the stomates of the leaves, right? Let's go back to just how does it get from the bottom to the top?
Are we going for like the thing that's in the plant or like?
No, it's just the property of water that helps it get there. I heard adhesion. So we got adhesion, cohesion, but together that makes the process of. Say again? Okay, hold on, we're doing good. So adhesion, cohesion, plus surface tension. So it's got a good surface tension. You guys have seen those water bugs, right? Water bugs that kind of stay, they don't fall through the water. So it's got good surface tension. All those come together to make, what do you call the teeny tiny veins in our arteries in your body? Thank you, capillary action. So like we're doing charades up here. Okay, capillary action is a property that water can really do very well versus like other things, other solvents like alcohols and oils. If I put some oil on the ground, the oil is not going to suck up into the plant, right? Oil doesn't have a very good, it doesn't have very good adhesion, cohesion, surface tension, hence it doesn't have very good capillary action either. So that's basically all we know about water. There's one more factoid, but I'm going to actually have you guys watch a video on this first, and so that's going to be kind of a starting point to us finishing this conversation on water. So, here we go. Ready? Write down factoids you don't know yet.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn.
What's the only one we didn't write down? High heat capacity, which we understand what that means. What's water's heat capacity at liquid? 4.18 joules per gram degree C. Great, good.
Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as
That little diagram where it was showing the water molecule kind of moving back, vibrating a lot. What was that water molecule getting ready to do? The liquid water molecule is getting ready to, say again? Phase change, right, to evaporate. So it's gaining more energy so it could break through the surface tension of the water because it's holding it in. All right, so here's the last little bit and then we're good.
lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
All right, so how much of that was new for you guys? New information. A little bit, a lot of it. Okay, you guys are so responsive today. We'll work on that. All right, so let's do the last part of solutions for now. We'll finish up the rest of this tomorrow if I find my correct part here. So, you guys, we just did this. This is going to be, actually, this is not related to solutions necessarily. This is a vocabulary term that you should write down. So, water is polar, right? And we have a group, I think, that's doing something like this with their science in a box. Water is polar, but it's a great solvent. Well, that means it dissolves very, very specific things. It doesn't dissolve everything it comes into contact with, right? So if I had an oil spill, does the oil just dissolve in the water, or does it float on top? It floats on top, right? Well, that means that water and oil are not mixing, and that's kind of common knowledge. You know that. You've seen it before. But, like, for example, if you have a dirty dish at home that's got some oil or grease, or, you know, maybe you had a nice fattening dish of some sort of dessert, it's got some oils on it, how do you get the oil off of your dish at home? You're right, you use soap. You wash it with something that's going to cause the reaction or cause something to happen between a water molecule and an oil molecule, or a fat or a lipid-based molecule. Normally they don't get together, but you have something that's called a surfactant or a surfacting agent. So a surfactant agent is something that stops surface tension from keeping water with itself. So if you can break the surface tension of water, water's like, oh, well, look, there's other things out here. I can interact with these other things, not just water like myself. And so the water tension being broken means other compounds can kind of intermingle with water, but doesn't mean actually they're going to like to intermingle, because it depends on their chemical properties if they like to intermingle or not. And what I mean by intermingle is intermolecular forces, like are they going to interact well? So you can actually force them to do even a better job of interacting by adding soap or other detergents, like that's how you wash your clothes. And there's a picture of it right here. I'm going to turn the lights off actually maybe one more time. Do you see the little zigzag line? That's like a big carbon chain. Think of back in biology when you guys drew your biomolecules. Didn't you draw like really long carbon chains for bats? CH, 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 CH. Do you know what I'm talking about? Okay, you guys are super responsive. Okay, so this is, this is your little fat molecule, and then this is your, it's sulfate, SO4. It's got a minus charge on it. That minus charge is an ion, right? And the ions really like to interact with water because of their polarity differences, which is what you guys were drawing in your lab yesterday. So this is a soap molecule. It actually can attract to water on one end and fat on the other end. It's like a little matchmaker. It's like, all right, I'll attach the fat on this end, I'll attach the water on this end, we'll come together and we'll go down the drain together, right? So it's just bringing them together so that they can actually intermingle very well. So that's called a surfactant. All right, so now we're going to transition to solubility. So here I have jokes for you. I always have jokes for you. Okay, I'm sorry, we just can't be together. Is it because I'm fat? Huh. This is a fat molecule. This is water. What would bring them together? A surfactant or soap. Okay. And then this one's, sorry, I thought a joke would break the tension. Boom, boom. Puddle on the floor. All right, you gotta be picking up what I'm putting down. Okay. Help! I'm dissolving, but bears are insoluble. That's easy for you to say. You're not polar. Yes. And then the name's bond. Hydrogen bond, which is not a bond, right? It's an attraction. Okay, I'm full of it today, guys. Okay, so last bit for today is going to be related to solubility. You would have received a solubility curve on your desk. This is yours. Please write on it. We're going to talk about these graphs shortly, but first we need to understand what solubility actually means. Yes. Is there anything more at your desk? Does everybody have one? Or at your desk? Okay. So solubility is a term that describes how much of a solute, so I'm trying to use that vocabulary so that you're understanding the difference between solvent, solute, solution, and so forth. So it's the amount of solute that can dissolve in a solvent to make a solution. So a solute that dissolves in a solvent to make a solution. But it's not just any solution. We call it a saturated, which if I have a paper towel, my paper towel is saturated. What would that mean in layman's terms? What do you think, Chloe? What do you think saturated would mean in layman's terms? Either of my Chloe's here. Okay, so a lot is a general term, right? Can I add more solute, or can I add more, like a paper towel being saturated, can I add more water to it? What happens if I add more water to a saturated paper towel? Okay, so it might break, or if I held it up, well, it might come out of the paper towel. Drips and drips of water, right? So saturated might be just perfect amount of water that's saturated up into the cotton of the paper towel. What would be an unsaturated paper towel? Jacob?
Just one that's like
okay, maybe that hasn't had any water added to it, or any things added to it. Maybe just a little bit, like a drop of water added to it. You guys have seen those Bounty paper towel commercials where they sweep it up. That little just spot on it. So unsaturated means it doesn't have full saturation. It doesn't have as much as it can hold. Saturated, like your brains get saturated after chemistry, it's full to the brim of knowledge. You can't add any more. Your head's going to explode. Saturated means it's at capacity. It can't add any more. Add any more of what? Well, we're talking about a solution, so I'm saying I can't add any more what? Solute. I can't add any more solute to my solution because it's at capacity. Well, you're going to see that there's a couple terms that we will utilize a bit more today and tomorrow. It's unsaturated, saturated, and supersaturated. And those are terms that give us a relative quantity of solute present in each of these types of solutions. Unsaturated means not at capacity. So can you add more solute? Yay or nay? Yay. Okay. I'm at capacity for saturated. Can I add more solute? Nay. However, you can artificially add more. It's called, you have to increase the temperature quite a bit to do that. And I'll show you a demonstration with that tomorrow. Supersaturated is over capacity. And I'm going to show you a graph of how that looks in a second. Okay. So, and these quantities that we're talking about, that's very specific to a temperature and a pressure. So if I change the temperature, the saturation point differs. If I change the pressure, the saturation point will differ. So we're really going to be focusing on temperature quite a bit, which is what you're going to see in your graphs. So when you look at a diagram of how does this saturated solution looks, does this look a little familiar? Something like this? Where did you see this? Yesterday. You were drawing yesterday. So if you need to modify based on some more things we're talking about today, do look at that. But you have your salt crystal, which a salt is just is a term for anything ionically bound. So a salt can be magnesium chloride, sodium chloride, copper 2 sulfate, can be anything ionically bound. It's just going to dissolve in water and create those attractions like you guys were drawing yesterday. But it's dynamic. What does it mean what does something mean if I say it's dynamic? Nick.
I don't know.
Where have you guys heard the word dynamic before?
Multiple things.
Okay, so I hear can do multiple things, how things interact. You have something else, Caroline?
Just like where we heard it.
Yeah.
Dynamic equilibrium.
Okay, so you've heard dynamic equilibrium where?
Honestly, I'm thinking back to middle school science.
Okay, so at equilibrium, we have a process is occurring, right? So the dynamic equilibrium word you see here is where the process of solute going into solution, that's a process, right? But we have some solute going into solution, meaning dissolving, some of it's depositing back to the solid. We're going from solid to aqueous, solid to aqueous, solid to aqueous. And so it's a constant back and forth, which is what dynamic means. It means it's ever changing, constantly changing. But at that point, if I have one particle that gets deposited, meaning it turns solid, and one particle that goes out into solution, has anything actually changed? If one makes a solid and one makes aqueous, and then one makes solid and one makes aqueous, has anything actually changed? No. But if I gave Jillian $1 and she gave me $1 back, we're giving people money, right? But she got her $1 back and I got my $1 back. Though if something's happening, nothing's happening. Does that make sense? It's called dynamic equilibrium because things are happening. It's just it looks like there's no net change because it doesn't show an overall change. We'll kind of see it. We'll talk about that a little bit more. All right, let's look at some graphs. So, looking at this graph here, you guys have a graph like this on your paper. Let's make some observations about this first. So the questions on your paper say, for which salt is solubility least affected by change in temperature? So take your best stab at that. Shout it out when you're ready. Which salt is solubility least affected by change in temperature? Nick. Say again?
CB2SO2. Oh,
this one is slightly different. You're right. So these are only the salts. Except there's a couple more salts on mine. So let me do you a favor. Let's look up here for a second here, okay? So here you'll notice that there's only salts here. The one on your paper has salts and gases. Go ahead. Sodium chloride. Okay, so let's look up here. You guys see sodium chloride right here? It has a pretty flat line here, right? So the flat line, what would you say my slope is there basically? Basically zero slope. Good job. And so zero slope here shows that for the change in grams of solute that's dissolved in water versus the change in temperature, what's happening as I increase the temperature on the sodium chloride solution? It's not really dissolving more, it's not really dissolving less, so there's basically no change on the salt solubility when I increase the temperature. So similar story, but let's reverse it. Who has the greatest change in solubility when I change the temperature? According to my graph up here for now. So who has so what are you looking for? So when you say the slope, what kind of slope? This has zero slope. This has, you don't have to quantify it. The what? Biggest slope. So steepest slope. Okay, so whoever has the steepest slope is going to be, in this case, what's the name of KNO3? Please don't spell it out. Potassium nitrate. Use your vocabulary, right? So this guy has got a really steep slope. So as I go from 0 degrees, I have how much to dissolve in solution? 10 grams of potassium nitrate. But if I go over here to 70 degrees, I have, like how much? 120 grams of potassium nitrate dissolved in 100 grams of water. And if I go even more, up to like 90, it's off the charts. It's up here like 170 someplace. So it has a very large difference in solubility as your temperature increases. So that's kind of how you read a graph like this. Going back to the questions on the sheet. For most salts, what is the relationship between temperature and solubility? For most of them. Darcy? Okay, so how do you see that described on the graph? So a positive slope, right? So most of our salts, there's potassium iodide. What's this guy's name? Sodium nitrate goes up. What's this guy's name? Ammonium chloride, and then this guy? Potassium chloride, and then ClO3, potassium chlorate. Most of our salts have a positive slope. So for all the salts which are ionically bound, as you increase the temperature, generally the solubility will also increase because of the nature of how does kinetic energy get transferred to the particles so they can kind of separate and dissolve. So it's related to thermochemistry just a little bit there. All right, last question, and this is on your graph now, okay, because I don't have gases on mine. What's the relationship between gas solubility and temperature in most cases? Look at your graph. How do the gases look on your graph? Right, hold on, go ahead, Emily. Right, so they're the dashed lines, right? So the gases are the dashed lines on your graph. They have a downward slope. So what does that mean about their solubility temperature relationship? Say again? Inverse relationship, right? So write this down for yourself. As you increase the temperature of the gas, the solubility is decreasing. Now, you've seen this in real life before. Who's ever drank a hot soda? Hot soda, it's not maybe ideal, but a hot soda, it's got a lot of bubbles, right? Very fizzy. Or is it really flat? If you left it out for, let's say you had, let me start over. I have a nice cold soda, pop the top, right? So the gas kind of fizzes out a little bit. But it's nice and bubbly. You got lots of carbonation in there. Let's say you open it, you drink some, bubbly, put it on the counter, a day or two later, finish that baby up. If it's been open, you're like 2 days later, what? So if you have left it open, most of it would be flat because the carbon dioxide that the bubbles are made of is probably going to dissolve out of the solution. That's because warm temperature does what with the kinetic energy of gases? It increases them, right? So if you have a warm temperature, you have increased kinetic energy of gases. And what does that do for their ability to break through the surface tension of their surface? More likely to break through the surface or less likely to break through the surface? More likely to break through the surface. So more kinetic energy of the gas molecules means breaks the surface, so it escapes. And as it escapes, there's less gas in the solvent, meaning the soda itself. Less gas molecules in the solvent. What does that mean about their concentration? Is their concentration higher or lower? If you have less molecules in a given amount of liquid, is their concentration higher or lower than what it was? Should be lower, right? So you have less of it, so their concentration is lower. So that's kind of walking through the steps of how does the gases have an inverse relationship versus the solids have a positive relationship. But all of this can be read from a graph as well. Okay, so I think from here, I might do one or two of these questions with you guys, and then I'm going to stop for now because I have a couple things you guys are going to do independently for the last bit of class. So at this point, this is on the back of your sheet. You following me? You good? Lies. It's on the bottom of the sheet. Yes. Solubility curves. It says line represents blank. Go ahead and write the line represents saturated solution. So my graph is a little different from yours, but I can go back. I can refer to the one that's on your sheet as well if the compounds are there. So question 1: how many grams of what's KBr? Potassium bromide will dissolve in 100 milliliters of water at 80 degrees Celsius. So look up here for this one because I don't believe is KBr in yours. No. Okay. So on my graph, look for KBr, and I'll try to make this a little bit bigger for you. Do you guys see KBr? Okay, so it's hard to see a little bit in the back, but you should see it right here. Okay, so how do you read a graph like this with the specifics given to us? How many grams of KBr will dissolve in 100 milliliters of water at 80 degrees Celsius? What do? You look for the temperature first. So the temperature over here is at 80. Go to the 80. Go up until you cross the line that we're looking at for specific to the ionic solution at hand, which is KBr. So this is our place where the 80 degrees mark matches with the saturated point of potassium bromide. And then you look and see how much is dissolved. So it's approximately, I'll be a little off there, but it's approximately 100 grams. So I'm saying 100 grams of KBr can dissolve, one second, in, and if you look at the axes very closely, in 100 grams of water. So this just so happens to be an equal amount. 100 grams of KBr at 80 degrees dissolves in 100 grams of water. So using that ratio, using that logic, if I had 200 grams of water, same conditions, how much KBr should dissolve? 200. If I have 300 grams of water, 300. So that ratio is relevant to the solvent at hand. So let's look at another one. I'm going to look at the number 2. How many grams of NaNO3, what's that called? Sodium nitrate. How many grams of sodium nitrate will dissolve in 500 milliliters of water at 10 degrees Celsius? So 500, let's look for sodium nitrate. We'll do that one in green. Here's sodium nitrate, which I think you guys have a graph of that as well. Mine might be a teeny bit different since I have a slightly different graph. But here's my sodium nitrate line. What temperature am I looking at? 10 degrees Celsius. If I go up to the saturation point, I see that's at 10 degrees Celsius, how much sodium nitrate dissolves in 100 grams of water? 80, right? So if 80 grams, it's kind of like a ratio, the 80 grams of sodium nitrate dissolves in 100 grams or milliliters, right? Because milliliters of water and grams of water are equivalent because of the density of water being 1. So if that's how much dissolves in 100 milliliters, how much should dissolve in 500 milliliters? How are you getting 400? Multiply what by 5?
Milliliters.
So I'm going to set it up in 2 ways first. Or I'm going to set up one way first. So I think what you're thinking is if you multiply this by 500 milliliters, that's essentially multiplying it by 5 because 500 over 100 is 5. But this gives me relevance to my cancellation of units again, where milliliters and milliliters cancel, and that gives me 80 times 5, which is, you just told me, 400. That would say then 80 times 5, so 400 grams of sodium nitrate, which is all 500 milliliters of water, at 10 degrees Celsius, because that's where we pulled our data from the graph. Give me a thumbs up if this is okay so far. Reading a graph and pulling information. Okay, so I got most of us. I'm going to pick this up tomorrow then. I'm going to stop for now. So here's what I have for you guys to do for the rest of the class. I have a couple of individuals that are going to be videoing, but I got one group I got to talk to. So in terms of finishing up a couple of things, I'm going to give you guys some options, but know that you'll be finishing them all. So you need to prioritize. So we go back to the first thing. So during your independent time here, you're going to finish your thermodynamics exploration, which is what you started yesterday. So if your Science in a Box group is good to go for their videos for this week, then go ahead and finish that. If you need to kind of proofread or prep your lesson, I have materials I need to gather them with you as we go. That's one thing we need to work on. If you have some questions on unit review or problem set 17, now's the time to work or ask questions. But know that you're going to be finishing one video, just a little bit of time on today. I have some people that need to video themselves. Finishing this is mostly at home. Mostly. I'm just going to get some questions in because I know that tutoring is a little rough with no teal, and then I have meetings and stuff after school. And the last thing is you're going to spend about 15 minutes today on the molarity worksheet. I'm going to put the molarity worksheet over here on the desk. So between your groups of Science in the Box groups, you guys need to decide what order you're going to accomplish these today. Okay? So I have 2 groups I need to talk to, EJ and Darcy's group, and then Maddie, Rishi, Miles, and Surprise. Okay? So I'm going to talk to those Science in the Box groups first. You guys, if you're going to the back, I'm going to help you with your massing. Oh, yeah, sorry. I don't know that. Oh, figures. So, Darcy, okay. So, you guys need, I gotta find you. You guys need, oh, you need I just don't have to see what happens in the next 2 days. Are you ready to get one of the things I should be doing today for yourself. Okay, we'll upload that to YouTube, and then I'll pass it off to the students, and I'll pass it to another topic. We're starting to report. That's a collaborative. Yeah, absolutely. That's like I want you guys have one today. So definitely playing the station, and also watch it. You could guys have maybe a hot right? Water, you want microwave. Okay, it would actually be a lot more. So we'll tell me DJ's group. You guys are going to video in the hallway since you're flying airplanes. Are you guys good to go eating or anything? Oh, we missed scale. Yes. And in terms of videoing, and then if you need others, we'll kind of group it together and you do a couple sections of the throwing and stuff. We'll kind of mesh together and get all the films. Okay? Oh, I can't find my, so, I think so. You can always modify. You guys need to have a laptop. Basically, you guys need to have a laptop. Hey guys, Subhash, come here. Can you guys need me right now?
We just wanted to know what are we doing with the center line?
You're finishing, the packets are in the lab station packet. For your videos. I have the schedule today. If you
need to freeze the ice.
I know, that's why I didn't have you guys do it today. I have a note to tell you guys to freeze your ice. I have a note for you guys to freeze your ice today. Yeah.
All right.
So I'll show you guys that in a second. Okay. Hey guys, so I made some comments on the Google Doc yesterday, 2 days ago. Have you guys had a chance to look at those?
I'm not ready.
Yeah, I think so. I would have to, if it mentions the, well, I don't know what account was, but regardless. So I had an issue because I was like, we talked maybe a week ago, and I told you, like, I can't prove that for you on this stuff, and issues with, like, being high level or low level, and so we were supposed to make some changes, but then I haven't seen a lot of activity at all from you guys on the document, and so it's been a little hard for me to get any feedback, and Sunday night, we made a ton of changes, and I still didn't have a lot of feedback from you guys. So
This is not like we're telling him. He wants to use it, but we're just helping them data information.
So that's what I can't see, and so that clarification is really important. So in terms of knowing what you're doing, are you going to sit there and look so you know what you're going to read for the video? So what do you need from me?
I'm trying to need an alka seltzer
So I'm going to give you guys, but I don't even know like how many sponsors, and I made some comments that needed to be resolved on the document, and so that's a work in progress, right? But I want to make sure you knew 100% what you're doing before you start video. So if you guys want to look at the document right now, if you guys can read it today, you can. If not, it'll have to be, it could be tomorrow. I'm trying to stagger this because we got a bunch of videos. Okay, so look at that right now. And whenever you get here, but just make you questions, make a comment on there. Thank you guys.